Hey everybody, it's Ripley again. We're on our last lesson. Woohoo! It's the end of Think. I hope you guys had a good one and a good time and learned a little bit about statistics, mostly statistics, a little bit of probability. Hope you enjoyed yourself. All right, we are in section 11.3. Look, the easiest way to do this is I'm simply going to do a problem for you. Again, it's going to be very much like the one in 11.2 because it's not very difficult, but to see it done out is the way to learn it. And we're going to do this with something called contingency tables. Contingency tables. All right, and I'm going to do problem number, let's see, we should do problem number 8 on page 577. This is going to be problem number 8. Okay, and so just take a minute right now, hit pause and read over problem number 8 for me. Okay, just give it a look-see and I'll meet you back here in just a sec. Okay, hopefully you had a chance to look this sucker over. And basically what we're going to do, it's real simple. This is called a contingency table or a two-way table. Okay, and let's talk about what we're going to do first. What we're looking for here is we're trying to figure out if wins and losses, we're checking to see if wins and losses are independent of an open or a closed roof. Okay, so are wins, losses independent of roof status? All right, I'm just going to write roof. Or are wins, losses dependent? In other words, does the status of the roof affect wins or losses? All right, that's all that we're testing. We're going to use the exact same test called chi-squared, which we know is the sum of observed minus expected squared divided by expected, right? Exactly the same thing. Now, the degrees of freedom, let's look at this. In this two-way table, what we have here are columns, right? Columns go up and down like columns on a building, and we have rows, all right? Now, the degrees of freedom in any, if we're testing for dependence or independence, you can say it either way. It's easy. It's always the product of the rows minus 1 times the columns minus 1. So in this case, it's really simple. We've got degrees of freedom equals 2 minus 1 times 2 minus 1. That's affectionately known as 1. All right. Now you may say, well, Ripley, what if there's not, if I'm missing a column? Well, then we're doing just a regular old chi-squared, and we're going to check for certain proportions in each of the wins and the losses. All right. Now, excuse me. So we're going to test this thing, I forget, in the problem. Yeah, the problem says we're going to test this guy at alpha equals 0.05. Now, let's talk about assumptions always. All right, assumption. Whoa, assumpts. Perfect. Assumpts it is. Yeah, it's the end of the semester. Leave me alone. The assumptions are exactly the same as goodness of fit. All right, in other words, of goodness of fit. In other words, we're going to have frequencies. We are randomly selecting values, although the values are already there. I don't like that this author chooses to write randomly selecting values. It's not as though we selected the values. What we did is we just stumbled in and we said, okay, we're gonna tally these frequencies. Okay, excuse me. Remember, so let's write them up. Number 1, so simple random sample, but I'm going to put a question mark there like, what does that really mean? Okay. Number 2, we're going to have frequencies in cells. So in other words, discrete numbers, frequencies in cells. And then last but not least, expected values in each cell, each cell greater than or equal to 5. Okay? All right, so the first thing that you want to do, I'm going to change colored pencils because or the color of my pen, because this is pretty important. The first thing that we want to do is we want to sum everything up. So I've got 51 in the first column, I've got 28 in the second column, I've got 53 in the first row, and I've got 26 in the second row. Now, we want a total here, and I'll show you why here in just a sec. We'll plug this in. You know what? I'm going to need to give myself just a little bit more room, and you'll see why in just a sec. Because you may already be a little suspicious. What did we say that this was? This was 53. This was 26. Gives me a total of 79. They both add up to the same thing. That's good. All right. Now you may say, what are these expected values? These are observed values. Those are just the values that go in, just like normal. But you may say, wait, where am I going to get my expected values from? Well, the expected values are actually really, really simple. The expected values for any cell is simply equal to, you ready? All I do is I take the total for the row that cell is in. I take the total for the column that row, or excuse me, that cell is in, and I divide it by the total number. All right? So I'm going to do these over here. For those of you that might remember matrices, I could go like the expected value of the cell in the first row, first column. You might see it written like that. The expected value, you know what, I'm going to change colors again. Let's go with orange, is going to be, so for this guy right here, the expected value in there is going to be, I simply take 53 times 51 and I divide it by 79. So I can't do that in my head, so I'm going to go 53 times 51 divided by 79, and I get 34.22. So that goes, I'm going to write that actually, I'll put it in parentheses so I realize that it's expected, and I go 34.22. Now you may say, wait, why is that the expected value? Well, think about that for just a sec. Basically what I'm doing is I'm taking 51, in this case, I could either do it 53 or 51. It doesn't matter. If I do 53 out of 79, that's the percentage that this row occupies in terms of the total. So 53 out of 79 is the percentage that row, that this guy right here occupies. But then I have to take that percentage and I multiply it times 51. And I end up with the the frequency value that this value should be. Now you could argue that exactly the opposite way. I could say that 51 out of 79 is the percentage that this column has out of the total, and then multiply it times the row total, and it'll give me what I need. All right. If I go E for the first row, second column, that's going to be 53 times 28. Divided by 79, and I'll go 53 times, what is it, 28 divided by 79, and I'm going to end up with 18.78. All right, and so on and so on. So E21 is going to be what, 51 times 26 divided by 79, so 51 times 26 divided by 79, and this is equal to 16.78. That's this guy, so 15.78. And then if I go E22, I'm just saying that that's the expected value of the second row, second column, excuse me, and I go 26 times 28, and I divide that by 79, and I get 9.22. And check those numbers. Of course, I could have screwed something up, but wouldn't be the first. So 9.22. Now, this chart is starting to look pretty nasty. So all that I'm going to do is I'm just going to cheat, and I'm going to go chi-squared is equal to, now remember what I'm doing. I'm going observed minus expected, so 36 minus 34.22 divided by the expected, whoops, excuse me, that should be squared divided by the expected, which is 34.22, right? Plus 17 minus 18.78 squared divided by 18.78 plus, because remember it's just the sum, just this guy, we're not afraid, whoa, just the sum, and then I'm going to go 15 minus 15.78 squared divided by 15.78. And then last but not least, because there's only 4 cells, what do I got? I got 11 minus 9.22 squared divided by 9.22. Okay? Now, do me a favor. You should be more than apt at using your charts. So think about what's going on. I'll give you a little break. I want you to think about what's going on. I want you to use the fact that the degrees of freedom in this case happen to be 1 and the alpha happens to be 0.05. I want you to use a chart. I want you to find critical values. We'll draw a little sketch here in just a sec. Figure this value out and figure out if we get to throw out the null hypothesis, all right? And the null hypothesis is it independent or not, okay? And think about what that means, because we're going to do a little write-up when we're done, all right? Give it a shot. I'll see you back. All right, well, dig my funky groove. First thing, I caught a little error that none of you guys yelled at me while I was recording. That should have been a 16.78, which, duh, I had written right here. So hopefully you got 0.806 for your chi-squared value. Remember that alpha equals 0.05, so if I stumble over to I just went to an online chart, which kind of makes it easy. If I stumble over to my online chart, apparently I need a 3.84 to make that sucker hum. All right, so what does that imply? If chi-squared, let's write this down. Let's see if I get her nice and big. So let's see, chi-squared critical was what was it again? 3.84. All right, so chi-squared critical is 3.84. So let's make sure we understand graphically what happens here. All right, remember what chi-squared looks like. I can start drawing these smaller by now. Hopefully you... Right? So if this area right here, if this area right here is supposed to be 0.05, right? And I know that this value right here for my chi-squared is 3.84. Well, look where 0.806 ended up. It's like right here, 0.806. It does not end up in our critical region. All right? So what do we write? Let's go to black. Since chi-squared equals 806 does not end up in our critical region. Now, another way to say that, now you got to be a little bit innovative here, because especially when you start doing some major research, you're not going to want to keep repeating yourself over and over and over again. So another way that we could put this is that chi-squared was less than chi-squared critical. Don't those imply exactly the same thing, right? Another way to say this is that our p-value was greater than 0.5 or 0.05, right? Because think about that. The p-value would be defined as everything to the right of this value 0.806. Don't forget, there's lots and lots of ways to play with this. All right? Okay, back over here, change my color again. Whoops, or we can just leave it on blue. There is no, wait, let's be official here. Let's be mathematical. We do not reject the null hypothesis. Remember, the null hypothesis said that wins and losses were independent of the status of the roof. Okay? Therefore, there is no evidence that whether the roof wow, good gracious, Ripley. Whether the roof, when these videos go down into posterity, they're going to be like, dude, what was this guy's problem? Whether the roof is open or closed, affected, right? Affected the win-loss status of the Astros. In other words, do whatever you will. Now, think about that. You got to think critically here. All right? When do you close the roof? When would you close the roof? Well, when the weather's poor, right? When it's crappy, when there's like drizzly, or it's in Houston, so there's probably not going to be a whole lot of snow, although I've seen snow in Houston, on television at least. You know what I mean? So if the weather's nice, leave it open. It's going to basically be the same as if the roof is closed. So really, theoretically, the roof status, the roof being closed, is supposed to mimic the weather if it's nice. You know what I mean? They should play about the same. All right, so hopefully this was an instructive little example for you. By now, you know how to use these charts. You know how to think statistically. Hopefully you've developed a keen sense of criticism about the way that statistics works. You know what I mean? It's real shiesty because you've got 0.05. You get to pick your alpha. So I can pick it at 0.05. I can pick it at 0.01. I always have students that'll come up to me, and we've discussed this in class, but it's always good to talk about. Ripley, when I picked alpha equal 0.05, I was significant. This is just in closing, right? But when I picked alpha equals 0.01, it was not significant. I'm going to get lazy here. It was not significant. What's the deal here? Well, it depends on what the researcher wants. I mean, if you think about it, what we basically have is a way to fudge the numbers, theoretically. Look, if you got alpha equals 0.05 and your t chi-squared value is not anywhere near the critical region, then there's no way this thing's going to get pitched out. But if you got something kind of in between, and you picked it at alpha equals 0.01 to start your research, and then all of a sudden you want a significant result, but it's not significant at at alpha equals 0.01, but it is significant at alpha equals 0.05. Well, if you've got hundreds of millions of dollars on the line in grants, you might be tempted to fudge the data a little bit. So hope you enjoyed the class. If we've got time, we may wave our hands a little bit about ANOVA, but we're not going to have any assigned problems out of there. So enjoy. It's great working with you all, and maybe we'll see you next summer. Bye-bye.